this is a thing we can work on in some later assignments. It's a very nice little problem. So let's say we sample 1,000 values from this distribution, and then take the maximum, right? And then we go back to the distribution, sample another 1,000, take the maximum, do that again, and then we're going to get a little distribution for the maxima. That has all sorts of beautiful math involved with this extremal statistics. But you can do some rough things to figure out typically how big will this largest value be, and similarly the smallest one. But we're interested in the largest one. And for power law size distributions, this is the number of samples that you've made. It grows as a power of that number. And so for a Gaussian, right, it's dying away like e to the minus x squared. The largest one, yes, it'll get bigger, but very, 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 very slowly, right? Really slow. It's really, constrained, and exponentials are really constrained. But these power laws, as you sample, and that's where things like the 100-year flood and the 10-year flood and the 1,000-year flood, those framings. So we have some of this in our general way we talk about, a natural phenomena. That's probably the best encapsulation of it, which is this sense that bigger and bigger things will happen over larger and larger timescales. And if it was a Gaussian distribution for flood sizes, we wouldn't have those words, right? And the way we talk about it mostly is that what was a 1,000-year flood happens every 100 years now, or every 10 years. Yeah. But this is going to grow. So for instance, that gamma equals 2, which is this cusp of a mean being infinite. It's a pretty extreme situation, right? This is actually going to grow like n to the 1. 1 over 2 minus 1 is going to grow like n. So the largest one in your sample is just going to keep growing and growing and growing and growing. So if you are thinking you're filling in some distribution, getting lots of samples, if you have a Gaussian, it'll just fill in and you'll start to see. We'll look at that later on with random walks. You can imagine all these little ball bearings doing random walks, and they fall and you count where they end up. Get a nice little normal distribution. Occasionally you get, you have to get all these coins being flipped heads to end up over there, right? You need to get 10,000 in a row to get way over there, but not with these things. So this is an important result. So if you have something like an exponential, as I said, then this is going to grow very slow, like logarithmic growth, which is very slow, not really moving, right? So we sample from our exponential. We will eventually, you get bigger things. You have to get bigger things, right? You start to get into the tail more, but it's going to grow very, very slowly. All right? So this is a good reflection of why this is a dangerous business. Yeah. You can't tell entirely where you're going to be in the future. And if you look at this, if you do the simulations, and maybe I'll have this later, then you'd see this sort of thing for your distribution. You sample more, and it has a tail. It keeps going out like this on a log-log plot. Right. Keeps filling out the tail. All right.